Space and time trade-offs. I'm Efina and I'll be presenting you this topic. The topics of discussion in this presentation are how space and time trade-offs is achieved by input enhancement, algorithms using input enhancement, which are the counting methods for sorting, and string matching algorithms. The sorting methods discussed under counting methods for sorting are the comparison counting sort and the distribution counting sort. The string matching algorithms discussed are the Horspool's algorithm and the Boyer-Moore algorithm. Space and time trade-offs in computational problem is achieved by using more space to store additional information obtained to accelerate the process of solving the problem. Consider an example, the problem of computing squares of integers. If time is at a premium when we receive a request, we can pre-compute the function values and store them in a table. For example, the square of 3 is 9 and it is stored in a 2-column table, and the square of 10 is 100 and these are stored in the 2-column table. So whenever a user request arises, it is just searching the value in the first column of the table and returning the value at the second column of the table. For example, if the user asks for the square of 10, browse to 10 in the first column and pick up 100 in the second column and return it back to the user. The idea is to pre-process the problem's input in whole or in part and store the additional information obtained to accelerate solving the problem afterwards. This process is called as input enhancement, which is used to achieve space and time trade-offs. Let us discuss two sorting algorithms using input enhancement. Comparison counting method for sorting uses input enhancement to achieve space and time trade-off. In this sorting method, for each element of a list to be sorted, it finds the total number of elements smaller than the current element and records the result in a counter or a table. And it uses the same counter to record the greater element than the current element. At the end of all the iteration, the positions of the elements in the final sorted array is represented by the values in the counter. Let us consider an example which has an input array of 6 elements. The elements being 62, 31, 84, 96, 19 and 47 stored in that order. A counter is declared as count array whose length is equal to the length of the input array. The count array is initialized to 0. At each iteration of the algorithm, each element of the array is considered and count is maintained for the lesser and greater elements in the count array. For example, at the first iteration, the first element in the input array is considered, which is 62. And the corresponding index position value in the count array at the first iteration will hold the value 3, considering the number of elements that are less than 62 in the array. In the first iteration, when you consider the array, 31, 19, and 47 are less than 62, hence the corresponding value in the count array is 3. The elements that are greater than 62 are 84 and 96, hence its count in the corresponding position in the count array is incremented by 1. In the second iteration, the second element in the input array is considered, which is 31. Down the input array, the number of elements that are less than 31 is counted. 19 is less than 31, hence the corresponding value in the count array is 1. Then the numbers that are greater than 31 is counted. 84, 96 and 47 being greater than 31, its corresponding count values are incremented by 1 in the count array. So in the subsequent iteration, 84, 96, 19 are considered, and the corresponding count values in the count array are incremented. Hence, the final values in the count array are 3, 1, 4, 5, 0 and 2. These numbers indicate the index position of the input elements. Hence, 3 indicates the position of 62, 1 indicates the position of 31, 4 indicates the position of 84, 5 indicates the position of 96, 0 indicates the position of 19, 2 indicates the position of 47 in the final sorted array. Hence, the final sorted array will hold the values 19, 31, 47, 62, 84 and 96 stored in that order. Comparison counting sort algorithm. The algorithm receives an array of orderable elements as input. The output of the algorithm is an array of sorted elements in non-decreasing order. As per the working mechanism of the comparison counting sort, the count array is initialized to 0. Then we have nested for loops. The outer for loop with the I variable selects the element in the input array which is compared with other elements in the array. The inner for loop with the j variable scans down every element down the array. The selected element and other elements in the array are compared. The count number in the count array is incremented based on which element is greater. Then, based on the final indexes that are stored in the count array, the element of the input array are stored in the sorted output array. The time complexity function of the comparison counting sort algorithm is derived here. The limits of the for loops becomes the limits of the sigma notation. And simplifying the sigma notation, the time complexity function is obtained as n multiplied by n minus 1 divided by 2. Hence, the time complexity of the comparison counting sort is big O of n square. Distribution counting sort algorithm. The distribution counting sort algorithm builds a frequency distribution table to achieve space and time trade-offs. It sorts array when its elements are repeated. Let us see an example for distribution counting sort algorithm. The input array consists of 6 elements with a range of numbers from 11 to 13. The frequency and the distribution table is built for the range of elements in the input array. The frequency of 11 is 1, the frequency of 12 is 3, and the frequency of 13 is 2. The distribution values are calculated for the range of numbers in the input array. The distribution value is the sum of the frequency of the element added with the distribution of the predecessor in the range of numbers. So the distribution value of 11 is 1 since its frequency is 1 and it does not have a predecessor. The distribution value of 12 is 4 since its frequency is 3 and the distribution value of its predecessor 11 is 1. Hence, we do a sum of 3 plus 1. The distribution value of 13 is the frequency of 13, which is 2, added with the distribution value of its predecessor, which is 4. So the sum of 4 plus 2 is 6. So we could notice that the frequency is the number of times the element occurs in the array, and the distribution values are the position for the last occurrence of this element in the final sorted array. This extra storage for storing the distribution value helps in the space and time trade-offs of the algorithm. The distribution value array, which contains the distribution values for the input range of numbers, will help to achieve better time complexity. After building the frequency and distribution table, the algorithm scans the input array from right to left. It places the element in the output array by selecting the indices from the distribution values of the elements in the frequency and distribution table. Hence, in the given example, when the algorithm reads the input array from right to left scan, the first element read is 12. Its distribution value is 4, hence 12 is placed at index 4 at the input array. After placing 12 at index 4, its distribution value is reduced by 1. Now the distribution value of 12 is 3. Now the next element is read, which is also 12. Now its distribution value in the distribution table is 3. Hence 12 is placed at index 3 and the distribution value is reduced by 1. Now the distribution value for 12 is 2. Now the next element read is 13, whose distribution value is 6. Hence 13 is placed at index 6 of the output array and its distribution value is reduced by 1. Next element read is 12 and its distribution value is 2. 12 is placed at index 2 of the output array and its distribution value is reduced by 1. The next element read is 11, whose distribution value is 1, and 11 is placed at index 1 of the output array and its distribution value is reduced to 0. Then the last element is 13 and the distribution value is 5. Hence 13 is placed at index 5 in the output array. Thus, the elements are sorted using the frequency and distribution table. The distribution counting sort algorithm receives an array of integers as input. The output of the algorithm is a sorted array in non-decreasing order. As per the working principle of the distribution counting sort algorithm, the values of the frequency and distribution table are initialized to 0. Then the frequency of each element in the input array is stored in the frequency and the distribution table. The distribution values of every element in the input array is calculated from the frequency of element in the input array. You may note that the distribution values represent the last index position of the elements in the sorted array. So, scanning the input array from right to left and picking up the indices from the frequency and the distribution table, the elements are placed in the output array. The time complexity of the distribution and counting sort algorithm is big O of n. You may note that this algorithm does not have any nested loop structures. String matching algorithms using input enhancement. Horspool's string matching algorithm. The Horspool string matching algorithm finds the input pattern in the text. It enhances the input by building a shift table for the input pattern and achieves better time complexity in string matching. The algorithm finds the input pattern in the text by considering 4 cases of matching the input pattern with the text. These 4 cases are derived by matching the last character of input pattern with the alphabet in the text by matching the pattern from left to right of the text. Let us consider the example of matching the pattern barber with some text. The pattern barber is spelled as B-A-R-B-E-R. The text is indexed from S suffix 0 to S suffix n minus 1. The last character in barber, which is R, is compared with some character at index C of the text. The Horspool string matching algorithm derives its 4 cases by matching the input pattern with the text from left to right. The 4 cases are derived by the matching of the last character of the input pattern with some character in the text. Case 1. If there are no C's in the pattern. For example, if C is letter S in the text, then we can safely shift the pattern by its entire length because S is nowhere found in the input pattern barber. Case 2. If there are occurrence of character C in the pattern but it is not the last character there, then the shift should align the rightmost occurrence of C in the pattern with the C in the text. For example, let the last character in the pattern, which is R, be matched with B in the text. B occurs in the pattern barber, but it is not the last character. Then B must be aligned to the rightmost occurrence of B in barber. Case 3 of Horspool's algorithm. If C happens to be the last character in the pattern and there are no C's among its other m-1 characters, then the pattern should be shifted by the entire pattern's length m. Consider the example of matching the pattern leader with some text. Here, the last two characters E and R found a match with the characters in the text, but D does not find a match. Instead, it found the character M in the text, and M nowhere is found in the pattern. Hence, the pattern leader is shifted to its entire length. Case 4. If C happens to be the last character in the pattern and there are other C's among its first m-1 characters, then the rightmost occurrence of C among the first m-1 characters in the pattern is aligned with the text C. So let us consider the pattern reorder. Here the last character of the pattern reorder R matches with R in the text. The next character E does not match with A, but R is present in the m-1 characters of reorder. Then R in the text is aligned with the rightmost R in the m-1 characters of the pattern. The shift table length in Horspool's algorithm is equal to the number of all possible characters, and each value in the shift table corresponds to the shift of that character. The shift of the character in the shift table is equal to the pattern's length m if C is not among the first m-1 characters of the pattern. The shift of the character is equal to the distance from the rightmost C among the first m-1 characters of the pattern to its last character otherwise. The algorithm for building the shift table is as given here. The input to the shift table algorithm is the input pattern of length m. The output of the shift table algorithm is the shift table whose length is equal to the number of all possible characters. All the values in the shift table are initialized to the pattern's length m. Then the distance from the rightmost C among the first m-1 characters of the pattern is noted and it is updated in the shift table in the corresponding position of the character. Let us match the input pattern barber with the text Jim saw me in a barber shop using the Horspool string matching algorithm. The shift table is built for all possible characters that would occur in the input pattern. The shift of the alphabets or characters that do not occur in the input pattern is equal to the number of alphabets or characters in the input pattern. The shift of the characters that occur in the input pattern is equal to the distance of the rightmost occurrence of the character in the pattern, and it is recorded in the shift table. For example, for the input pattern barber, A position is 4 from the rightmost character. R position is 3 from the rightmost character, leaving the last character, that is R. B position is 2 from the rightmost character and E position is 1 from the rightmost character. Hence, in the shift table, for the character A, the value of shift is 4. For character B, the value of shift is 2. For character C, the value of shift is 6, since C does not occur in the input pattern. Hence, for all the alphabets, the shift is 6 if it did not occur in the input pattern. So let us match barber with the text, Jim saw me in a barber shop. So the matching occurs from left to right. So at first, the last character in the input pattern is compared with the text character. Here, A does not match with R, and the shift of A in the shift table is 4. Hence, the input pattern barber is shifted 4 positions to the right. Now, the last character in the input pattern R aligns with E in the text. The shift of E in the shift table is equal to 1, hence the input pattern is shifted 1 position to the right. Now, the last character in the input pattern R is matched with space in text. Space has a shift of 6 in the shift table, hence the input pattern is shifted 6 positions to the right. Now, the last character R aligns with B in the text. B has a shift of 2, hence the input pattern is shifted 2 positions to the right. Now, R matches with R, but E does not match with A. The shift of A in the shift table is 4, and now the input pattern barber is shifted 4 positions to the right. Now, the matching proceeds from the rightmost character to every character in the pattern with the text. The match is found. The algorithm of horsepool string matching is as given here. The input to the algorithm is the input pattern and the text. The output of the algorithm is the index of the left end of the first matching substring. If no matches are found, it returns -1. The shift table is built for all possible characters that would occur in the pattern. Using the looping structures, the pattern is matched from left to right of the text, and shift values are used for shifting the pattern from left to right. The time complexity of the horsepool algorithm is equal to big O of nm, where n is equal to the number of characters in text and m is equal to the number of characters in the pattern. Boyer-Moore string matching algorithm. The Boyer-Moore string matching algorithm uses two shift tables. The first one, the bat symbol shift table, is based on the shift table built for horse-pool string matching algorithm. The second one is the good suffix shift table. The shift table for pattern barber, which we built in the horse-pool string matching algorithm, is as given here. The bat symbol shift in Boyer-Moore string matching algorithm is based on the shift table in horse-pool string matching algorithm. So, if the pattern barber is searched in some text and match the last two characters before failing on the third character, which is letter S in the text, the pattern is shifted by T1 of S, which is the lookup value of S in the shift table, minus 2, which is equal to the number of characters that are matched before failing in the match of the character. Hence, the bat symbol shift now is equal to 4. If the pattern barber is searched in some text and the match the last two character before failing on letter A, we can shift the pattern by T1 of A minus 2, which equals 4 minus 2, that equals 2 positions, and this 2 is the bat symbol shift. The good suffix shift of the Boyer-Moore string matching algorithm is built by matching the prefix and the suffix substring in the pattern. The prefix is the substring that occurs in the beginning part of the pattern, and the suffix is the substring that occurs in the ending part of the pattern. The good suffix shift is the distance between the start position of the matching suffix substring and the prefix. Let us build the good suffix shift table for the pattern ABC BAB. Selecting the suffix from the end of the pattern, which is B at position 6, it matches the prefix at position 4. Hence, the good suffix shift equals 2. Considering the suffix AB starting at position 5 matches the prefix at position 1. Hence, the good suffix shift equals 4. Considering the suffix BAB starting at position 4 does not find a match of prefix for the entire suffix, but a substring of the suffix, which is AB, matches a prefix at position 1. Hence, the good suffix shift equals 4. This is proceeded for the suffix CBAB and BCBAB. Boyer-Moore string matching algorithm. Step 1. For a given pattern and the alphabet used in both the pattern and the text, construct the bat symbol shift table. Step 2. Using the pattern, construct the good suffix shift table. Step 3. Align the pattern against the beginning of the text to start the string matching. Step 4. Repeat this step until either a matching substring is found or the pattern reaches beyond the last character of the text. Starting with the last character in the pattern and comparing the corresponding characters in the pattern and the text until either all the M character pairs are matched or a mismatching pair is encountered after K character pairs are matched successfully. In the later case, retrieve the entry T1 of C from the C's column of the bad symbol table where C is the text mismatched character. If K is greater than 0, also retrieve the corresponding D2 entry from the good suffix table. Shift the pattern to the right by the number of positions computed by the formula D equals D1 if K equals 0 or max of D1 and D2 if K is greater than 0. Here in this formula D1 equals max of T1 of C minus K and 1. Boyer-Moore string matching algorithm example. The pattern considered for matching is BAO BAB. The Boyer-Moore string matching algorithm builds the bad symbol table and the good suffix table before starting the string matching. The bad symbol table and the good suffix table for the pattern BAO BAB is as given here and it is constructed as described earlier. Boyer-Moore string matching algorithm begins the string matching by aligning the pattern from the beginning of the text. Here in the example, when BAO BAB is aligned from the beginning of the text, the last character B does not match K in the text. Hence, the shift is equal to D1, which is calculated as T1 of K minus 0, which equals 6, and BAO BAB is shifted 6 positions to the right. Now, the last two characters AB matches the character in the text, but the third character B does not match the underscore in the text. Hence, calculating the D1 and D2 to find the shift value D, we get D1 equals T1 of underscore minus 2, which equals 4, D2 equals 5, and max of 4 and 5 equals 5, and hence the pattern BAO BAB is shifted 5 positions to the right. Again, the match is found for the last character B, but the second character A finds a mismatch with underscore. Hence D1 is calculated with T1 of underscore minus 1, which equals 5, and D2 equals 2. Hence the shift is max of D1 and D2, which equals 5. Hence the pattern BAO BAB is shifted to the right by 5 positions, and at this position the algorithm finds a match of the pattern with the text. To conclude, in this presentation we discussed how space and time trade-offs could be achieved by input enhancement in the sorting methods and in the string matching algorithms. Thank you.